For my third redo of standard 3.1, I chose to do problem 3.5, and asked us to consider a spin 1/2 particle with a magnetic moment at t equals 0. The state of the particle is in spin up on the z-axis. So part A asks if the observable s sub x is measured at t equals 0. What are the possible results and the probabilities of those results? So we want to find the eigenvalues of the relevant observable. In this case, the observable is s sub x, just like the question stated. The eigenvalues of s sub x are plus or minus h bar over 2. So these are the possible results of the measurement. To calculate probability, we can use our usual definition to calculate probability. So we'll take the inner product of spin up on the x-axis with spin up on the z-axis. So that's our function that's going in with our function that's our wave function going out. And then we find that our probability is 1/2. Same likewise for probability of measuring spin down on the x-axis. So next, part B. Instead of performing the above measurement, the system is allowed to evolve in a uniform magnetic field. B equals B naught y hat. Calculate the state of the system in the SC basis after a time t. First, we want to diagonalize the Hamiltonian to find its eigenvalues and eigenvectors. The Hamiltonian for a system in a uniform magnetic field is this when our magnetic field is defined as B naught y hat. So our Hamiltonian is defined as this, where mag naught is E B naught over mass of electron. Thus, our eigenvectors are plus and minus, or spin up and spin down on the y-axis, and the eigenvalues are plus and minus h bar over 2. I got those by going through these equations. Next, we want to calculate the state of the system after a time t. So we need to switch to the basis of the Hamiltonian. In other words, we want to write our wave function at t equals 0 in times of the energy eigenstates. We know that our quantum state at t equals 0 is spin up on the z-axis. So rewriting this in terms of our energy eigenstates, we have so we go through, we want to figure out how to rewrite this. So here I add our spin up and spin down on the y-axis kets, and I find that they're equal to 2 over root 2 times spin up on the z-axis. So in order to get this to just be spin up on the z-axis with no constant front, I can multiply it by root 2 over 2, or simply multiply it by 1 over root 2, and that will give us our energy eigenstate. So this will give us our initial wave function in terms of our energy eigenstates. Now we multiply each eigenstate coefficient by e raised to negative I e naught t over h bar to get our wave function at time t, or quantum state at time t. So going through that, we multiply the wave function by e raised to negative I e naught t over h bar, and then we plug in for, or e sub n, so that's our energy eigenstate. We plug in for our energy eigenstates that we found. So that's plus and minus h bar mag naught over 2. Plug that in. Now we finally can switch back to the z basis. And here are again our kets for spin up and spin down on the y-axis. So using those, we switch back to z basis, and we find that this is our state of the system after time t. So next, part C. At time t, the observable s sub x is measured. What is the probability that a value h bar 2 will be found? So again, we just use our definition of probability. We know that s sub x is uh, pot when its eigenvalue is h bar of 2 when it's positive on its spin up on the x-axis. So using that, we can just use our usual definition for probability and take the inner product of the bra of spin up the x-axis with our quantum state ket, and we find that this is our probability that a value of h bar of 2 will be found. Part D just asks us to draw a schematic diagram of the experiment in parts B and C. So here is a schematic diagram. It's a Stern-Gerlach detector, and then we have our spin 1/2 particles coming in, and they are detected going spin up on the z-axis. They go through, and then they are affected by a magnetic field, B naught, y hat, and they go to this final detector, and we have probabilities of 1/2 times 1 plus sine omega naught t, and 1/2 times 1 minus sine omega naught t. So this is my standard, my third redo of standard 3.1.